Hi, my name is Georgi Raduf, and I want to consider this question, which asks us to plot the transfer characteristic of this circuit. So the transfer characteristic is the relationship between the output voltage and the input voltage. So if I plot it here, what will be the relationship between output and input? Now we'll approach this question first intuitively to understand what this circuit is, and we will make a strategy on how to approach it, and we'll calculate at the end the transfer characteristic. Let's look at the circuit. Now we recognize here an inverting amplifier configuration, so this part of the circuit. Then what we have is also this part of the circuit, which is called the limiting circuit or the clippers. So what we see is that if one of these diodes conducts, then this 3 kilo ohm resistor will come in parallel with the feedback resistor of 60 kilo ohm, and this will effectively reduce the gain of the circuit. So this diode usually can be modeled as a switch that is turned on or off when the forward voltage across the diode becomes 0.7 volts, which is given here. So if this becomes 0.7 volts, and the direction is very important, please note the direction, here is positive, here is negative, then the diode can be considered as a switch that is closed. For any other voltages, so basically reverse biased or voltages less than 0.7 volts, then the diode is modeled like a switch that is turned off. It will connect effectively or disconnect the limiting circuit to the feedback of the amplifier. So if the diodes are off, then the limiting circuit will be switched off, disconnected from the input, and I'll have certain gain because this will be given by just the inverting configuration of this op amp. At certain moment, the diodes will turn on, and then the 3 kilo ohm resistor, either this one or this one here, will connect and will limit the gain. This is the clipping effect, and our goal now is to define what are these voltages for which the clipping takes place, so V input limiting minus and plus, and what are the respective output limiting voltages. If we know this, we will also know what is the slope here, the gain in the middle section when the diodes are turned off, and what is the gain at the outer section when the either diode is turned on. Let's first look at the diode. So the simple model that we'll use for the diode is like a switch that activates when the forward voltage is 0.7. So I can now here draw the volt ampere characteristic of the diode. This is the voltage in this direction, and this is the current of the diode. If the voltage across the diode becomes 0.7, the current will explode. So there are two now regions for operation of the diode. One is when the diode is off, or the switch is off. So for all negative voltages, and for small positive voltages that are up to 0.7 volts. The diode is like a switched off. I can just remove it from the circuit. The other region of operation is when the diode is like a switch which is turned on, then the current goes very high because the diode conducts. And this happens when the voltage is more than 0.7. Now, because I have these two modes of operation for the diode, or at least I can model, then I can consider the circuit with these two modes when either the diode is off or when one of the diode is turned on. Now, when the diode is, so diodes are off, this for sure happens when the voltages at the input are very small. If the voltages tend to 0, the output will tend to 0. So this will be a positive voltage, so definitely the voltage drop across the diode will not be positive 0.7. And then the diode will be off. So this will be, I can just simply remove this from the circuit. And I have now just a inverting amplifier configuration. The output network here is only loading the output. It has no connection now to the input, so it cannot influence the transfer between input and output. Now, the relationship between the output and the input is defined by the input resistor and the output resistor. To get it, we have to understand now the concept of virtual ground. Why this node is at 0 volts or very small potential, 0, for all practical purposes 0. Now, the output voltage is given by this op-amp. This is ideal op-amp. And it will be the gain of the op-amp, which in the ideal case is infinity or something extremely large, and then the multiplied by the difference at the input. So this is V plus and this is V minus, the inputs, V plus minus V minus. This is extremely large, infinity. This V plus is connected to ground, so it's 0. Now, to have a finite V out, we need to have this extremely small, ideally 0. 0 times infinity is of course undefined, and then we will define the output, so the output can be anything, and then we define the output through the input. But if it's difficult to work with infinity and zeros, imagine that this is extremely large thing. So to have a realistic V out that will not explode, finite V out, this means that the difference between the inputs should be extremely small, something extremely small. And we say that with this such a negative connection, we say that the inputs are virtually connected, which means that if one of the input is ground, then this node here should be at the so-called virtual ground or 0 volts or something extremely small. For all practical reasons, we can assume this to be 0. And now it's very easy to get the relationship between the input and the output. Just look at this current. This is an ideal amp and there is no current flowing here, no current flowing here. So all the current that flows from input to the output goes through these two resistors. So I can now write that the potential difference between the input and the output divided by the resistance between both, 90 kilo ohm, is actually the current. And this current is also equal to the input current. It's the same current. And the input current is of course V in minus 0 divided by the resistive part of the current, which is only 30 kilo. Alright, so now I can simplify a little bit. and I get that V out is equal to minus 2 V in. So now I have the slope, I have the gain for very small voltages, and this slope is delta V out divided by delta V in is minus 2. Now, good. Let's see the condition when this diode turns on. Say that this is voltage VA here. This is 0 volt. And when VA gets minus 0.7, then the difference between the input in this direction, the input of the diode and the output of the diode will be 0.7, and this will be the border when this gets, the diode turns on. So when VA will become minus 0.7, so if VA is equal to minus 0.7 volt, the diode on. Alright, now VA is between 15 volts and V out. VA is connected to V out through a 3 kilo ohm resistor, and VA is connected to 15 volts power supply through a 9 kilo ohm resistor. When at the border, when the diode turns on, there is no connection here. Yeah, so this is no connection. Then VA is determined, is somewhere in between V out and 15 volts. Now, if V out reduces, VA will reduce too, yeah, with certain portion. So this will become negative. If it becomes sufficiently negative, this diode will turn on, will connect this 3 kilo ohm in parallel with 60 kilo ohm, and the gain of the amplifier will reduce. So let's try now to express VA in terms of V out in order to get the conditions for V out to get VA minus 0.7. So look at this voltage divider here, this resistive path. Then I can write 15 volts minus V out, so this is the total current that flows here, divided by the resistive path, which is 12 kilo ohm, 9 kilo ohm plus 3 kilo ohm, is equal to 15 volts minus VA, so this is this path here, the same current, divided by 9 kilo ohm. Simplifying a little bit, so if this is divided by 3k, so 3 and this is 4, then I have now a relationship between the voltage VA and the output V out. So now let's simplify a little bit. 3 times 15 minus 3 times V out is equal to 4 times 15 minus 4 times VA, right? And then I can write that VA is equal to 15 fourths plus 3/4 of V out, right? And now I'll substitute this with 0.7. So when VA becomes 0.7 volts, yeah, or just 0.7, let's not make mistakes. Then I will have the V low, the V out limiting level. Yeah, so this will give me, if I calculate it properly, let's see, times 4, so this will be like 0.7 times 4, and then divided by this 3 minus 15 divided by 3 is V out low. All right, so V out low now can be calculated. I'll just do it here to be minus 5.933 volts. Okay, now I have V out low. So this is this node, V out low. This is minus 5.933 etc. volts. Now we see that the circuit is symmetrical like this, so this is the same as this. So if I calculate now the conditions for this diode, I'll get actually, yes, you know, plus 5.933 volts. I have the slope here of minus 2, so I can get actually what is now this level. So let me change the color. So this will be, this here will be 5933 divided by 2. So this will be 5933 divided by minus 2. This will be minus 297 volts. So this here will be plus 927 volts. Yes, and now I can calculate what is this slope. And when one of the diode is turned on, my circuit will be like this. $60 kilo ohm and then 30 kilo ohm. And one of these, either this diode or this diode, will be in parallel with the 60 kilo ohm. Yeah. So now the gain V out divided by V in will be, of course, 60 kilo ohm in parallel with 3 kilo ohm divided by 30 kilo. Yeah. And you can calculate this. So 16 parallel V out. So this is this part, and then times 30 kilo. Let's see what I'll get. So this is K, 1K from here. This will go, so this is 10. This will be just 6. So I have V out, V in, 6 divided by 63. Yeah. This will be minus, I have here minus 0.95, whatever, 0.95. Yeah. So then this slope here, delta V in, delta V out divided delta V in, will be 0.95. Yeah. So we have in the middle high gain of minus 2, and then after these levels the gain dropped to 0.95. So let's recap the transfer characteristic. The relationship between the input voltage and the output voltage. When the diodes are not connected, we have a high gain, and the gain is determined purely by this network. At certain moment when the output voltage becomes too low, so when the output voltage gets very low, this node VB gets very low, and this node VA gets very low. This diode is still off, but this diode can turn on, and then the gain drops. The gain here was calculated to be minus 60 kilo ohm divided by 30 kilo ohm minus 2, while the gain at this point was calculated to be 3 kilo ohm in parallel with 60 kilo ohm divided by 30 kilo ohm. So something like 0.095, of course with a minus sign. And this happens for V out low, which is minus 5.93. Yeah, so this will be for V in limiting 9297. Yeah, so the limiting circuit is symmetrical, so we have this gain exactly the same, minus 0.095, and this happens at voltage V out low equal to 593 volts. This would be minus 297. So this is the transfer characteristic. Thank you very much for your attention. Bye.